All right, back to 9.3 for some more talking about how you can arrange a circuit. We talked about last time arranging things in series. The second option is interesting, was arranging things in parallel. If you notice, I've changed up the way the metal bands are attached here. I've got metal going on both sides of this, attached to both of these attached, both of these attached. So all of these are now attached together on both sides. So because of that, I can now do the following. If I put the positive end, or negative end, doesn't matter which, down here, and I put the negative end, say, here, or here, or here, or here, or here, but not here, but here, I get what's called parallel. And parallel is the way the house lights in your house are set up. If one light bulb goes out, it does not take out your whole entire house, right? You don't go on around going, hey, which light bulb works? Like you would have to do with Christmas tree lights. Also, the effect of one affects not the others. You'll notice they're all brighter. That's because they're each getting the full 6 volts, okay? If I were to unplug one, okay, it had theoretically has no effect on the other one. Of course, I think my battery's dying because it looks like it does have an effect. Oh, poor battery. The battery is dying. So that should have no effect at all. Let's see if I can do it this way. What if I do the second one? Yeah, that's, well, you know, hey, it's looking like it's having an effect there too. The battery is not doing its job. Let's see if I got a better battery here. Hold on. Probably got a worse battery here. Should check these out ahead of time. But theoretically, it shouldn't change at all unless your battery's just about on the edge of death, which this one might have been. Maybe this one's, oh yeah, much brighter everywhere, right? So if I unplug one, no effect at all, right? So this battery's junk, going in the trash can, I swear to you. I just put it in the trash can. Okay, again, unplugged, doesn't affect the other ones at all. Again, each one is getting the full 6 volts, so they don't care what's going on. Why do they get the full 6 volts? Because if I'm an electron and I'm here, if I go through this light, I get to go back to the battery now. I'm done. I don't have to go through two more light bulbs. If I go through this one, so each one's getting the same treatment. Each electron can use the same amount, use its full energy going through just one light bulb. Also, what's interesting about this is the current. See, if there is, let's say it's a 1 ohm light bulb, which is not, but let's just say it is, then 6 amps would be going through here, correct? 6 volt battery. 6 amps are going through here. And 6 amps would go through here, 6 amps go through here, which means the batteries provide 18, which means the amount of current is changing to part of the circuit. Battery, 6 goes this way, 6 goes this way, 6 goes this way. And if 6 goes, each one of 18 amps coming back in the battery. What leaves the battery is the same as what comes out, right? But what goes through each one of these could be different. If I had a different brightness light bulb, light bulb with a different resistance in it. Let's see if this one, I don't know if you'll be able to tell the difference. See how much dimmer that one is? Okay. It's still getting 6 volts. Why is it dimmer? Because its resistance is higher, so it's letting less current through it. So this one has less current than these two. Okay. So in a parallel path, the fluid, as Ben Franklin thought it was, it's really charges flowing through a wire, coming out of the wire, come into here, and they split. Some goes through here, some goes through here, some goes through here. These two have the same amount because they happen to have the same resistance. This one has a different amount because it has greater resistance, so less electrons are likely to go through there. But some still do. It's not a short, right? Okay. Good so far? Okay, let's do this with some physics and ease mixed in with it. All right, so if you're a basic parallel circuit, that's what we call it when you do this, you have a resistor here and a resistor here. So let's say I have a 12 volt battery, and let's say this is 6 ohms and 2 ohms. We don't tally up the resistance the same way. We don't. Why? Because each one gets its full voltage. So effectively, the resistance of the system is actually lower than, if some can get through here, then it's actually less resistant than just the 2 ohms by itself. All right? So before we do that, let's talk about what happens in terms of voltage. I have to lose all my volts going through just this one resistor. So I can do V equals IR all by myself here, and I would find that my current through that one resistor is 6 amps. Same thing, I look here, I've got my voltage through here. I've got that my current coming through here would be equal to V equals IR. 12 equals I times 6. And I'd end up with my I being, what was it going to be? I lost my train of 2 amps. Okay. Now you're thinking, well, phew, I still like to have that total resistance thing going for me. And I don't blame you. It's actually kind of handy in things we're going to do in the future. But I have to figure out what my total resistance is. Well, total resistance is a little tricky for this because it's not just adding it up. What is it? Well, if I think about it in these terms, I go, look, I need to lose all of my voltage through each one of these individually. Then the total current, okay, the total current can be gotten by doing my voltage divided by R1, let's say the first resistor, plus my voltage over R2. And now if I remember that voltage total equals current total times resistance total, I could do a lot of mathage and I get voltage total equals voltage over resistance 1 times resistance total plus voltage over resistance 2 times resistance total. Is that right? I did that right? Okay, good. Then these voltages are the same, right? Voltage is the same for each case, so I just divide both sides by voltage, and I get 1 equals resistance total, and I'm going to pull that factor out my resistance total, 1 over resistance 1 plus 1 over resistance 2, and so I get 1 over resistance total equals 1 over resistance 1 plus 1 over resistance 2, and plus dot, even though that's not part of my proof, that's actually how you find the total resistance. So if I wanted to, I could jump right to how do I find my total resistance for this thing? Well, resistance 1 over resistance total for this particular case would be 1 over 2 plus 1 over 6. Now, this is a physics class, so common denominators. What are we talking about? I have no idea what we're talking about. You don't do that at all. We would actually put this in our calculator and decimalize the heck out of it. Instead, what I'm going to do is I'm just going to go ahead and do it with common denominators. I think that's fair, because after all, you do know the math for that. This isn't a math class, though, so you can get away without doing that. So this becomes 3/6 plus 1/6, which is 4/6. Now, that means my resistance total, when I flip, I get 6/4, which is 1.5. You're thinking, okay, so that's my total resistance. How does that help me? Well, voltage total equals current total times resistance total. So my voltage total, which is 12, is equal to my current total, which is, I don't know. Resistance total is 1.5. I do a little math. I get my total current is equal to 8 amps. And indeed, if you realize that this had 6 amps going through it, and this had 2 amps going through it, right? Then what has to be coming down this wire is 8 amps, and this thing has to be acting like one resistor that is 1.5 ohms in ability. Alrighty then. You should have already done 3. Number 4 says on 9.8, it says 3 30 ohm resistors are connected in, and in bold is the word parallel. So suddenly you have to deal with parallel, okay? So what I'd like you to do is do 4, 5, 6, 7, and 8. I have a video, which I'm going to attach after this, which I think does 4 and 5, okay? But obviously try 4 first, get it right or wrong, and then check your answer using the video, then do 5, and then check your answer using the video, and then you should be good to go. All right, how are we feeling? If you get done with this and you go, Mr. Resney, I need more help, then that's not even close. Could you try a little bit? Send me a post, whatever, and I will do whatever I can. If your question is more specific, I help you a little bit better than if your question is, what? Okay, then I can't. It takes 15 posts before you even figure out what you're talking about. Okay, so let me know as best you can what you need, and I will happily help you with it. All right. Let me see if I can pause this. Nope, I'm pausing today.